So Cambridge has lots of past year papers that are available online. When the marking schemes are all available for any paper, for paper 1, they don't detail how to come up with the best or correct choice, alright? So in this video, we will deal with paper 1. I took this from the O-Level Physics Syllabus 5054, component code 12 in the May-June 2016 series. If you have done this before, proceed with this video, but if you still haven't, I suggest that you try the paper first. I have embedded a link in the description of the video. Try answering the questions and go back to this video for the concepts behind the correct answers, right? Now, for question 1, a golf ball is roughly a sphere like this, and that the question is on the circumference of it. We know that the circumference can be calculated using 2 pi multiplied by the radius. Alright? However, the question is specifically asked for the instrument that reads the circumference, not to determine data to be used in calculation of the circumference. Calipers, micrometer, and ruler, these can give the radius we need in implementing the formula 2 pi r. But the tape is the only one that can be fitted along the circular distance here and reads the circumference without calculation. The answer here is D. Alright? Now, for question 2, when given mass and force, acceleration, which is being asked in this question, can be calculated using the formula A equals F over m, the Newton's second law of motion. Be careful with this formula, as this requires that F here is not just any force, but the resultant force, the sum of all forces acting on the object. Alright? Now, for resultant force, people recommend the use of free body diagram, like representing an object with a dot and drawing forces acting on that object from the dot. Alright? Here, we have the dot representing the sledge. The horizontal force can be an arrow pointing this way, and the friction pointing opposite to that. We know that the mass, this one, and the forces 60 Newton and 20 Newton. Let's write those here, 60 Newton and 20 Newton here, which gives a resultant force of 40 Newton. To find the acceleration, this resultant force will be divided by mass, which is 25 kilograms from the problem itself. 40 divided by 25. By the way, I wrote it like that as this is anyway equal to a Newton. And that I want you guys to see that because this is divided by mass, the kilogram will be discarded, leaving only the unit meter per second squared, which is a unit of acceleration. Alright? So 1.6 meter per second squared is the answer, and this is B in this question. Now, question 3 is asking for the direction of the resultant force. But I am seeing that I have to go through another formula for acceleration first. This one, which is directly taken from the definition of acceleration, rate of change in velocity. The V here is not a speed, otherwise it will appear that there is no acceleration as there is no change in speed here, constant speed. I also understand that you probably used speed before in calculating acceleration, but take note that it is only applicable on motion where an object is traveling along a straight line. Okay? Acceleration is on velocity, which is a vector having both magnitude similar to speed plus a direction. A change in direction, even without change in magnitude, as in the case of this question, gives us an acceleration. Consider this point and this point. When object moves in a circle, the direction of velocity is always tangent to the curve, alright? Like this arrow when center of the car is here, and this when it is already here after some time, okay? The delta V, or change in velocity, is the final velocity, this arrow V, minus initial velocity, this other arrow here. Now, in notation form, we can write V minus V, but this should not equal 0 as we are operating with directions, not just magnitudes. It would be good if we can use graphical method in this case, alright? We draw the final velocity here, then we add the negative of the initial velocity, this arrow. Mind you, V minus V is also the same as V plus the negative of V. This is what we have in the diagram. We added the negative of the initial V. Now, this arrow, from the tail of the first arrow to the head of the second arrow, represents the change in velocity. Now, from the formula here, it appears that the direction of delta V tells the direction of the acceleration. Similarly, the direction of the acceleration tells the direction of the resultant force, as implied in this formula a while ago. Alright? So, our answer in this case is option B. In a constant speed motion along a circle, the delta V, the acceleration, and the resultant force all point towards the center of the circular path or curvature. This question is about inertia, this property mentioned here. And inertia is related to mass. That is, the more massive an object is, the more resistance to change in state of motion there is. Alright, the answer here is B. This question is about the instrument to measure weight and to measure mass. You can actually get some clues from the instrument's name, like this one, Newton meter. If you are familiar with the voltmeter or ohmmeter, you know that this voltmeter measures a quantity that has a unit volt, which is a voltage or potential difference, alright? And this ohmmeter measures a quantity that has a unit ohm, which is resistance, alright? A Newton meter, therefore, based from that idea, measures a quantity that has a Newton at its unit, which is a force, alright, F. And weight is an example of a force which is a product of mass and acceleration due to gravity or gravitational field strength G, alright? Looks like these two options A and B cannot be our answer, leaving us either C or D as answer, alright? Now, let's analyze this beam balance here. The principle of moment tells us that the sum of counterclockwise moments, in this case, W1, D1, where D1 is this distance, equals the sum of clockwise moments, which is in this case the W2, D2, where D2 is this distance. Alright? We can expand the equation here to give mass 1, G, D1 equals mass 2, G, D2. In a beam balance, these distances are equal, so we can just remove these D1 and D2 here. And obviously, these masses in this instrument are in the same gravitational field. So we remove these G's also, as they are also the same. This leads us to the idea that a beam balance is used to compare the mass, alright? Say this mass 1 to a known mass, this M2. Alright, C is the answer to this question. This question is about the conditions of equilibrium. There are two conditions. The first one is that all forces must be equal to 0. And the second condition is that all moments equal to 0, which we already covered in the previous question here. Okay? We can determine the correct answer to this question using any of these two conditions. But the first condition is simpler, as it's easy to see that force F here, this one, should be upward with magnitude equal to 12 plus 8. This satisfies the first condition of equilibrium. Our answer is B. Okay? Now, time is a scalar quantity, and so do the fundamental quantities like length, mass, and temperature. These three are all derived quantities, alright? In the case of speed, V is equal to distance, which is length divided by time, a scalar quantity divided by another scalar. The resulting quantity, or the speed, therefore is also a scalar. So this is also cannot be an answer. For energy, we have many types. Let's just think of one, kinetic energy, which is half mass times square of speed. Speed is a scalar, and that the square of scalar is also a scalar. So the V squared here is a scalar. Mass is also a scalar. A scalar multiplied by another scalar yields a scalar quantity also. Alright? So energy is also a scalar. This cannot be an answer as well. Alright? Now, how about force? We use A equals F over M in the previous question, and that can be written as F equals MA also. M is a scalar, and A is a vector. It has a direction as explained earlier, and that the direction is the same as the direction of the resultant force. Alright? So we answer B here. Force is a vector quantity. We have two types of nuclear reaction. Fission is the splitting of nucleus into smaller ones, or fragments, and fusion is combining smaller nuclei to form a larger one. Reactions or changes happen inside the nucleus, and when it do, it emits a great amount of energy. Our sun is dominantly consists of hydrogen atoms, alright? Due to the condition in the sun, these H atoms combines to form helium atoms, and the process is called fusion. Our answer here is C. For this question, we use the formula work equals force multiplied by distance or displacement. But note that before using this, make sure that the object's displacement is along the line of force. Alright? If this is the direction of the force, then work can be calculated when you consider this distance along the direction of the force. 300 Newton times 5.0 meters gives us 1,500 joules of work. The answer here is C. Alright? Now, here, we should first recognize that the atmospheric pressures are the same in all beakers. They are all open here. Pressure is exerted by the atmosphere, but since they are all the same, we don't bother ourselves about those, alright? We will just use the formula pressure is equal to rho GH, where G is 10 meters per second squared, a constant, and rho is density, which is also a constant, since all here are made up of the same liquid. Alright? H is the depth measured from the surface of the liquid down to the point we want to know the pressure. Since all these are constant, we can say that pressure is directly proportional to the depth. Here, we can see that the point is the deepest relative to the surface. Alright, and therefore has the greatest pressure. The answer is C. This question is again about pressure. Say this is the object. This shaded portion is the area. On that area, a force is exerted equal to the weight, W. And by definition, pressure is force over area. But this force is the weight W divided by that area A. B gives us the pressure here. Alright, this question is about Boyle's law. At constant temperature, the product of pressure and volume is constant, or P1 V1 equals P2 V2. At the surface, the volume is 6 and pressure, not 0 but equal to the atmospheric pressure. We write 1 here. Note that there is 1 atmospheric pressure in 10 meters. There may be a slight variation, but it should be about 2 atmospheric pressure 20 meters below. And in addition to that, there is 1 atmospheric pressure at the surface, giving us 3 for P2 times the volume we want to find, this V2 here. Then you simplify this. V2 is 6 divided by 3, or 2 cubic centimeter. The answer here is 8. A requirement in choosing a substance to be used in a thermometer is that it must have a property that varies linearly with the temperature. In liquid in-glass thermometer, a constant, say M, is the change in temperature divided by a change in volume. Whenever the temperature varies, a linear change in volume also happens because of that. Imagine the temperature increases, the volume here expands and takes this space in the thermometer P. In the other thermometer Q, assuming that it also have the same temperature change, its volume expands the same way. However, because the space here is bigger, then you will see this only, which obviously makes this thermometer P more sensitive. Alright? Because you can do more calibrations in here. Okay? Now, imagine that the temperature rises again. The liquid expands here also, and here, and so on. In the other thermometer, those expansions are going to be these, alright? These ones, alright? Occupying only those spaces. This means that there are still room for expansion at higher temperatures here. Unlike in the other thermometer, with it can only measure up to that end point. We can say therefore that the range of this thermometer Q is larger, alright? Alright, I missed this question, sorry for that. The idea here is that at constant volume, pressure is directly proportional to the temperature. Option D cannot be an answer as this implies no constant volume. We have a fixed volume here. P, or the pressure, is the frequency of collision of particles on walls, alright? Since the gas is heated and the temperature rises, then frequent collisions are expected. It says less here. So option A cannot be an answer. The molecules do not expand. We cannot answer this as well. Molecule sizes are the same. Expansion is explained by the distances among these molecules and not the change in their sizes based on the kinetic model of matter. Our answer therefore is option C. They move faster as temperature increases and that the temperature is proportional to the average kinetic energy of molecules related to their speeds. Alright, for this question, let's see if conduction happens here. Conduction requires a direct contact between the source of heat and the material to be heated. We do not have that here, so conduction is not happening. These options, therefore, A and B cannot be an answer. Alright, how about convection? Convection is the transfer of heat through the movement of heated material, which is usually upward because of the decrease in density when heated. But since the bread is beneath the source of the heat, then convection is not happening there. Alright, this cannot be an answer. Radiation is the electromagnetic wave, and wave transfers energy in all directions. So in our case here, the answer is D. Now for this question, we need to know what happens to the air particles close to the cooling unit. Cooling means energy is taken out of a substance, and that in doing so, particles move closer to each other, an opposite to moving away from each other when the substance is heated during expansion. We have two possible options here that can be an answer to the questions. These, alright? The other column will tell exactly which one. The density is equal to mass per volume, and here we see that density is inversely proportional to volume. When air cools down, the particles move closer and therefore occupy smaller space, smaller volume. Therefore, density increases, explaining why they move downward. Alright, our answer is D. The hint here in this question is the idea that frequency remains the same when wave goes from deep water to shallow water. Alright? Imagine this boundary between deep water and shallow water here. We can draw the wave using arrow like that, and due to change in depth, wave bends like this. Alright? Another way to draw or represent the wave is to use these lines perpendicular to the arrows. These ones here, these ones. You can also see this when you do an experiment in ripple tank, alright? These lines represents all the crests in one part of the wave, usually called the front, alright? Since fronts are basically crests, then we can also say that the shortest distance between two consecutive fronts is the wavelength, or lambda, here, alright? And here also. Now, we know that the speed is wavelength times the frequency. If frequency is constant, then the change in wavelength, as seen here, corresponds to the change in speed also. Alright? Both wavelength and speed changes as the wave goes from deep to shallow water. Alright? The answer is D. By definition, this line, which is 90 degrees with respect to the boundary between mirror and air, is the normal line. So we have two possible answers here, A or C. The correct answer is on our understanding of the angle of reflection, which is measured between the normal line and the incident ray. That means this 40 degrees here, alright? Our answer is A. Now in this question, you might want to think back about the three major rays that we can use when doing ray tracing techniques. This ray, when bent by the lens, always passes through the focus, lying in the principal axis, alright? This is the focus. The focal length, by definition, is the shortest distance of that focus from the center of the lens. This one, alright? Which is also this length, option B. This question is also about lens, the types, converging or diverging. Here and here, the rays are as if they are being forced to meet at one point, alright? Here and here, the same thing. It looks like when you extend the refracted rays, they will meet or converge at a certain point. Okay? However, here and here, the rays are not being forced to bend inward. Instead, let's erase this. Bending is such that they are being spread out, like those, alright? Based on the effect of the lens here, we can say that this first lens is a converging lens. Same with the second one, converging lens also, but the third one is a diverging lens. It is trying to spread out the rays, alright? Option B is the answer. Here we need the Snell's law. Snell's law states that the index of refraction a constant for a specific material is the ratio between the sine of the angle of incidence to the sine of the angle of refraction. Now, based on the diagram, it looks like angle W is the angle of incidence, alright? And angle Y here is the angle of refraction, which tells us that option A is the expression for the index of refraction here. Okay? Here, okay, we know that wavelength is the distance between two consecutive identical points in a wave. In the diagram, you should see that this part is identical to this part, and they are consecutive, alright? Therefore, this is the wavelength, option B. We look back at our conventions for magnetic field lines going from N pole of the magnet to the S pole. We can draw those like this, and this one, and all these things, this one's also, alright? Okay, the needle in a compass is a magnet, and it aligns itself to the magnetic field lines. It looks like the compass in this question should be here at option C, this one, alright? Pointing this way, okay? Now, remember that during charging, electrons are the ones transferring. It is unlikely to be the protons, since it is going to be very hard to take those from the nucleus. And even if you could, the material changes as there will be different proton or atomic number. After rubbing, the cloth becomes positively charged, alright? Meaning it has now less negative or lost some electrons. Alright, this means that the answer is option A. Negative charges, which are electrons, are transferred from the cloth to the other material. Now here, we will use the equation for current. I is equal to Q over T. We have 45 coulomb over 180 seconds here. Alright, we do this conversion for the time because ampere, which is the unit among the options, is defined as coulomb per second, not a coulomb per minute. Alright, so 45 over 180 yields 0.25 coulomb per second, or 0.25 ampere, which is option A. Now for this question, imagine we have a resistor here. The potential difference by definition is the work done per unit charge, as the charge move from one point, alright, across the resistor. From this defining equation for potential difference, we also have the definition of volt, following the formula, which is 1 volt equals 1 joule per coulomb. Option B is the answer. Okay, now, the combination of three 1.5 volt cells in this diagram gives us a voltage equal to just 1.5 volts. They are connected parallel to each other, alright? If you did that in series, then the total voltage is 4.5 volts, alright? In parallel, it will be just 1.5 volts. Even if you disconnect this one, it's still 1.5 volts. You disconnect the other, it's still 1.5 volts. Now, why is it that people choose to use this combination of 1.5 volts cells and still get 1.5 volts as a result? The answer is because when they do, they get that same voltage and the battery life will last longer. Alright? Option A. Okay? Now for this question, the concept behind the correct answer is this. The equation for power equals to the product of current and voltage. However, in using this equation, and you want to find the power of the lamp, then the I, or the current here that you need, is the current that passes through the lamp and the voltage across the lamp. Alright? Let's check the options. In A, current is correct, but the voltmeter gives the EMF, not the voltage across the lamp. In option C, the ammeter is wrongly connected. Same with the voltmeter, it's wrong. In D, ammeter is connected properly and reads the current passing through the lamp, but the voltmeter is wrongly connected. Option B gives us the proper position of voltmeter and ammeter, and that the values are what we need in the formula. Alright? For this question, remember that when we have a parallel connection, the total voltage is the same with the voltages across each branch. Alright, like total voltage equals V1 equals V2 and so on. Alright, depending on the number of branches. Alright, in series, the total voltage is the sum of all the individual voltages of the components connected in series. Here we have 6 volts. This branch also have 6 volts. Same with this last branch. Alright, we have identical resistors also. So we can say that these two here have 3 volts each from the total 6 volts, and in this last branch, the 3 identical resistors have 2 volts each. Alright, total to 6 volts as well. When you use the voltmeter here, alright, and place in A, what you will read in the voltmeter is the voltage between these 2 points, which is 3 volts. Alright? Now, this question is on the use of 3-pin sockets or plugs. Standard arrangement in this manufactured device tells us that the earth wire is properly connected. Same with the neutral wire and the live wire positioned properly with the fuse. There is an issue with the cable cover though, as it is supposed to be under the clip, like this one. The answer here is A. Alright? Okay, we start with this unit of electricity. This one actually refers to 1 kilowatt hour. Alright, remember that. Actually, it is from this definition, P equals the energy per unit time. When rearranged, this one gives us energy which can be considered as 1 unit of electricity. In our case here, where P is 1 kilowatt hour and time is 1 hour. Alright? Now the problem is telling us that the rate is $0.24 per 1 unit of electricity or 1 kilowatt hour. And the cost, therefore, is whatever energy consumed multiplied by this rate. Alright? Now, the energy consumed is 100 watts times the time, which is 5 hours per day in 21 days or 3 weeks. Cancel these. And we have 10,500 watt hour or 10.5 kilowatt hour. Alright? Now, using that in the formula for the cost, we should get $2.52. This is option C. Now, this question asks about how to change the direction. Alright? Make it opposite. And also make the rotation faster. When we switch this on, current or the conventional current flows here. And that if we have to make the diagram bigger, this wire, we have the magnetic field here, symbol B. The direction of the charge is responsible for conventional current here. Alright, this arrangement gives us a force acting on the charge or the wire itself. The force can be determined using the left hand rule. Thumb here, first finger, alright, second. The rest we do not need, alright. The first finger points to the direction of the field B or the magnetic field, alright. The thumb points to the direction of the force F. This can only happen if your second finger is pointing the direction of the charge, producing the conventional current. Alright? That rule applies in determining the direction of the force. The magnitude of the force, however, depends on how strong the current in the field, and also how many loops you have in the motor. More loops, greater current, stronger magnetic field, all these can make the magnitude of the force greater. Alright? Why do we need to consider the magnitude of the force? Because this is the one responsible for the rotation. Alright, in option A, magnitude of force is increased, meaning faster rotation, but do not change the direction of the rotation. This cannot be an answer. Alright? In B, you can see from the hand rule that if you direct the second finger and the first finger opposite to before, the force's direction remains the same. So this cannot be an answer also. In C, reversing the magnetic field using the hand rule makes the force reverse its direction. Okay? And therefore, rotation should go opposite to that. Alright? However, decreasing the current only makes the magnitude of force weaker and therefore gives slower rotation. Option D directs the force opposite to before and its magnitude increases with current. Therefore, faster rotation. This is our answer. This hand rule is called Fleming's left-hand rule, and in this next question we can also use that. If we imagine the charges generating conventional current here, each of these charges should experience a force which would have an overall effect to the wire. Alright? Magnetic field, as I already mentioned earlier, goes from N to S pole, and so the direction is this. The direction of the charge, remember, conventional current is this way. Now, using this Fleming's left-hand rule, you should see that the finger representing the direction of the force points into the screen or into the page. So the answer is A. Alright, we again need the formula for electrical power here. The P is equal to IV. When voltage is high, the formula tells us that if we assume that power is constant or changes are negligible, then the current will be low. Alright, from here we can remove these two options, A and C. Now the correct answer can be determined using the other formula for power. P is equal to I square R. The cable itself has a resistance, and that the power in the cable can be considered lost during transmission. If you only have a small current in the cable, the formula for power here implies that power loss is low. Alright? So this option can also be discarded. Our answer is D. At high voltage, current is small, and that because the current is small, power loss in cables is low. Now here, thermionic emission is the process where free electrons are emitted due to high thermal energy. When this filament heats up, electrons jump out of the surface and likely go to the particles here. The particles then become negatively charged, and since these negatively charged particles are attracted to the plates, we can say that the plates are positively charged. Alright? The answer here is C. Plates are positive, and that this phenomenon happened because the temperature of filament is high. Alright, we have a series connection here, meaning the EMF is equal to the sum of the voltage drops across each resistor, provided, of course, the source doesn't have any internal resistance. We can write it like this: epsilon, representing the EMF, equals V1 plus V2. The EMF is 6 volts, and that the voltages here should be 3 volts and another 3 volts here because they both have the same resistance and they receive the same current. Now, when this is increased, the current through both resistors remains the same. Alright, they are in series. But the V2 here will be larger because it has now larger resistance. Alright, V is equal to IR. Alright, at higher resistance, higher voltage reading. The answer is B. Alright. Now 37. This question is about alpha particles. They are similar to the helium nucleus, having 2 protons and 4 nucleons. If a certain nucleus ejected an alpha particle, it means that the nucleus loses 4 nucleons and 2 protons, or -4 and -2. Alright? Which gives a new atom, this one, option A. Alright? Ionizing effect implies the ability to influence the electrons in something, alright? The fact that alpha has positive 2 charge, beta has negative 1 charge, and gamma has no charge, there is greater effect from alpha, followed by beta, then gamma. Alright? Positive 2, negative 1, and 0. The answer is A. 39. This is about the definition of half-life. Alright? This should be very easy for all you guys, as option D here is basically how half-life is defined. Okay, we come now to the last question, and this last question is about isotopes. Isotopes are characterized by same proton number and different number of neutrons, which also means different nucleon number, alright? We see that we have 2 protons here. Here we have 3, and here we have 2. Meaning, atom P and atom R are isotope of the same element. So the answer is B. Alright? Bye.